This video is about medians and altitudes in triangles.
So we're going to start by discovering what a median is. This asks us to find the midpoint of each side of this triangle that's on the coordinate plane. Two of them I can see just by looking at the graph. So one of them is here at 3, 1, and the other one is halfway through this vertical line at 6 and 2.5. And then the other one I'm going to calculate using the midpoint formula. So for the slope line there, 0 plus 6 over 2 and 1 plus 4 over 2 gives us the midpoint 3, 2.5. So that's approximately right there. So I've calculated my 3 midpoints. And now the instructions say connect each midpoint to the opposite vertex. So I'm going to switch colors to do this. Take the midpoint the last one we graphed, that's at 3, 2.5, and connect it to the opposite vertex of the triangle. So that means the vertex that is across the triangle from it. Then we'll do the same with the other two, connecting it to the opposite vertex. And then make an observation about the segments that you just constructed. Hopefully you'll notice that they all go through the same point. That means that they are concurrent lines, and that point that they go through is called the point of concurrency. So these lines that we just drew in green are called the medians of the triangle, and they all intersect at the same point. So median of a triangle connects a vertex to the opposite midpoint. And of course, we just constructed 3. This picture shows 1 median drawn. So it's got this to show that we found a midpoint. And then it connects it to the opposite vertex of the triangle. And that's just 1 median of this triangle. Of course, all triangles have 3 medians. The 3 medians are concurrent at a point that is 2/3 along the way from the vertex to the opposite midpoint. So these have an interesting relationship. The point that we're talking about is called the centroid. That's the special name of this point of concurrency. And as shown on this picture and these statements that are underneath the picture, each median is sort of divided into 2/3 and 1/3 on either side of the centroid. So for example, this line DJ, this median here, has C 2/3 along the way, so that if this were, let's say, 8, then from C to J would be 4, because the whole line would then be 12, and it's broken into 2/3 and 1/3. Or you can think about it as DC is double JC. So let's use this. In the diagram at the right, we have XA being equal to 8, and it asks us to find the length of XB. So this is kind of a giveaway since I just used these numbers. But if you were in a different scenario, the way that I would recommend doing this is to set up the 2 sides of your median as 2x and x, because you know that that's the relationship between those 2 pieces. Because sometimes they'll give you the smaller one, sometimes they'll give you the longer one, sometimes they'll give you the full length and ask you to find one of the pieces. So if you always get in the habit of labeling them 2x and x, you can apply this in any scenario. Here they give us the XA, which means we can write that 2x equals 8. Solve for x, we get 4. That means now we know the 2 pieces, so XA would be 8 and BA would be 4, and put them together to get XB. So XB will equal 12. It's not always this simple. Sometimes there's a little bit more involved, but if you always get in the habit of using 2x and x on your label, you should be able to figure out the right equations to use. An altitude of a triangle, this is a different segment, is a perpendicular segment that connects a vertex to the line containing the opposite side. So we have perpendicular segments that don't necessarily bisect anything, so that's what makes this one a little different from the other ones that we've been doing. An altitude is simply perpendicular, connects the vertex to the opposite side. In an acute triangle, like the first one here drawn on the left, if you take the vertex that's up at the top and connect it to the opposite side by forming a 90-degree angle, it'll look something like this. And it looks like it bisects it, but it does not necessarily need to bisect it. All that needs to do is connect the vertex to the opposite side, forming a 90-degree angle, and that's called an altitude. This triangle has other altitudes. I'm going to erase that one because it's a little bit easier to see one at a time. So let's say I want to connect the bottom right vertex to its opposite side of the 90-degree angle. Well, this time your instinct might be to go like this, but as you can see, that's not going to form a 90-degree angle with the other side. So you want to think carefully about forming a 90-degree angle with the opposite side, And you'll realize that this altitude looks something more like that, because there is the 90-degree angle with the opposite side that you're trying to create. So altitudes are some of the hardest ones to draw, just because it's a little bit, it's not as natural as drawing some of the other ones. You have to really think, before you put your pen to paper, about reaching the other line and forming a 90-degree angle. So in an acute triangle, the altitudes are inside the triangle. On a right triangle, as you can see here, some of the altitudes are actually on the triangle. So this altitude is the side of the triangle. Same thing here. If you tried to connect this to the opposite side, it would be on the side of the triangle. And then a right triangle also has one altitude that's inside. That would be if I tried to connect this to the opposite side, and it would look something like that. So in a right triangle, you have two altitudes that are actually on the sides of the triangle and one inside. In an obtuse triangle, you have one altitude that's inside, right? And this one just goes straight to the bottom. But the other two altitudes may actually lie outside of the triangle. So if I'm trying to connect this to that line over there but form a 90-degree angle, you actually have to draw an imaginary extension of that side of the triangle in order to form the 90-degree angle that you're looking for. Boy, that came out a little sloppy, but you get the idea. Sometimes the altitude has to be drawn outside of the triangle, which again just leads to this more kind of unnatural feeling about drawing altitudes. They are pretty challenging to draw. Just like the other lines we've been learning about, three altitudes are concurrent. The special name for this point of concurrency is the orthocenter, and it may be inside, outside, or on the triangle, depending on the type of triangle you have. So there could be an acute triangle with an orthocenter inside. A right triangle has its orthocenter on the triangle, and an obtuse triangle will have the orthocenter outside. So these are nice computerized versions of altitudes, which look a lot neater than the ones that I was trying to show you. So let's find an orthocenter. We are given triangle ABC with vertices 1, 3, 2, 7, and 6, 3. So let's see if I can plot point A is right there at 1, 3. Point B is at 2, 7. And point C is at 6, 3. Okay? And I'm asked to find the coordinates of the orthocenter. So remember, to create an orthocenter, you need to be drawing three altitudes, which are a little tricky to draw. I'm going to start by connecting these dots as neatly as I can to create triangle ABC. And I will label it. Oh, that was not A. That was B. This is A, and this is B, and this is C. And in order to get the orthocenter, I need to create three altitudes. So an altitude needs to go through a vertex and be perpendicular to the other side. The easiest one to draw is the vertex B connected to the side AC. Because in order to create a 90-degree angle with AC, I just have to draw a vertical line, since AC is a horizontal line. So there's one altitude, but actually, because this triangle is acute, we should have established at the beginning. The orthocenter we're looking for is going to end up being inside of this triangle. The other two are a little bit harder to draw. So we want to do a little bit of calculation to figure out the other two altitudes. For this one, I know that I need to go through A, and I need to be perpendicular to the line EC. It's going to look something like this, but that's not exactly precise. So I'm going to do a little bit of calculation. I can figure out the slope of BC by using the slope formula. So if I use B and C with the slope formula, it'll be 3 minus 7 over 6 minus 2, which is negative 4 over 4, which is negative 1. I now know that the slope of BC is negative 1, which means the opposite reciprocal slope would be positive 1. So the line, the altitude that goes from A over to BC must have a slope of positive 1. The point that it goes through is the point A, which is located at 1, 3. And so now I have enough information to write the point slope equation of that line. And then get it into slope-intercept form. And now I have a much more precise way of calculating the orthocenter of this triangle. This equation that I just wrote is the equation of this red line right here. This red altitude that we tried to draw is much more neatly done now that we know the equation of it is supposed to be y equals x plus 2. Now I can find the point of intersection of this with the other one that I drew without having to find the third one, because if all three are going to be concurrent in the same place, you really only need to draw two of them to find the intersection point. Because now I can see that both lines go through a nice whole number, I can tell that the orthocenter of this triangle is going to be 2, 4. The algebra that we did over here was all just to make sure we were as precise as possible about finding it. It may have looked like a whole number, but unless you're using algebra or really good measuring tools, you want to back it up so you're sure that you have the right coordinates. So that's the orthocenter of ABC. And that is all.